This video will give you a high-level overview on timing classification of digital systems. In digital systems, signals are classified based on how they are related to the local clock. Why local clock? Actually, there are two types of clocks which are called global clock and the local clock. The global clock is the clock that takes the clock signal to every part of the integrated circuit, to different blocks and circuits. But local clock is the one which really makes the system synchronous. So two blocks which are not at all related may not have synchronization. So that means local clock need not have synchronization with the global clock. So there is no need of any relationship between the local clock and the global clock, right? So it is only the local clock that is needed for synchronization purpose. So there are two types of signals that transition at predetermined instant of time, and the signals that can transition at arbitrary instant of time. In the first one, we have classified them as synchronous, mesochronous, and plesiochronous. You might have heard of synchronous, but you may not have heard of mesochronous and plesiochronous. We are going to discuss about them. And asynchronous, we have heard of asynchronous as well. The word synchronous directly represent what it means. Every element in the circuit is in sync with the clock, right? Chron in English means related to time. So they are sync with the local clock with respect to time, right? That's what the synchronous means, and asynchronous is the opposite of that. So this is the synchronous interconnect. The signals with exact same frequency as the local clock and maintain a fixed phase offset with a local clock is called as synchronous interconnect or synchronous signal. So if you can observe here, this is R1. Let me take the laser pointer. This R1 is register 1 and this is register 2. So it is a register to register. We call it as reg to reg path, right? This is a register to register path, and there is some combinational logic, whichever the gate may be, AND gate or gate, something like that. We have some combinational logic in between this. So this is the local clock we are talking about. We don't care about how it came here, this clock. Which global clock is driving this clock doesn't matter, right? We just care about this local clock, and our signal Cin, which is generated from this input, has to be synchronized with clock. That means only if it is a positive edge triggered flip-flop, if it is a register, then only at the positive edge of this clock an input can transition to the output, right? So this is definitely synchronized with respect to this Cin is definitely synchronized with respect to this clock. And if you observe this C out, there is a restriction for C out to enter register R2. That restriction is provided by this local clock again. And there is one more thing, which is nothing but the period for which the C out is valid. That is also decided by this clock, right? That in turn boils down to the fact of setup and hold timing. I don't want to discuss them in detail, but there is some time for which this input to the register R2 is not valid, which is the propagation delay of this signal itself. So that is restricted, and after that this register R2 samples this signal with respect to the clock. Only at the positive edge of the clock this C out can sample the signal, and it can transfer to the output. So the length of the uncertainty period places an upper bound on how fast the system can be clocked. So the uncertainty period consisting of both setup and hold timings. We will discuss about setup and hold timing in future videos. So this uncertainty period places an upper bound, which means the frequency cannot be more than the frequency of the setup and hold timings. If my setup time is some 4 picoseconds and hold time is 1 picoseconds, I have 5 picoseconds, and 1 by 5 picoseconds is around 0.2 terahertz. It cannot be larger than that, right? So I cannot have a lot of uncertainty period which is set up in whole timing. Next is Mesochronous interconnect. In the previous thing we have said, in synchronous interconnect, we have said signals with exact same frequency as the local clock and maintain fixed phase offset. That phase doesn't change, right? We know there is a fixed phase. We don't have to have exact same phase that of the clock. What do we mean by that? We can have some delay after this comes. When clock positive edge comes, this data need not be sampled at the same time. It can be sampled at a little more than after this comes, right? So it can have certain phase difference between, there can be certain phase difference between scene and clock, but it should be fixed. This propagation delay should be fixed. Then only we can say that it is synchronous. These kind of circuits are always common. You might have heard of this always, but mesocronous interconnects come when we are dealing with the high level integrated circuits with a lot of complexity within it. So when do we see this mesocronous interconnect? Signals with same frequency as the local clock, but with unknown phase offset. So the phase offset is unknown here. For example, clock domain crossing. A single integrated circuit can have multiple blocks such as block A and block B, and these blocks might have been driven by different types of clocks, right? Clock A and clock B. They might be of same crystal oscillator, but their characteristics may be different. They might have been traversed some different paths. So what may have happened is their phase is not equal. Their phase is not fixed. The phase difference, they have same frequency. Okay, the clock A and clock B has same frequency because they're generated by a single crystal oscillator. But the thing is, they don't have fixed phase offset. So because of that, what happens is R2 cannot sample the output of this interconnect, output of this R1 directly. There might be some mechanism to make that, to eliminate that phase difference always. So that is achieved by this variable delay line, and there is a control. It takes the input from this signal which is coming from R1, after that interconnect delay, and it also takes the clock P input. It compares both of them and eliminates that phase difference by using variable delay. It delays the signal more so that it comes in sync with this clock B. So the output of this variable delay line will be in sync with clock B. The phase is fixed with clock B, right? This is what it achieves. And the third one is Plesiochronous interconnect. Now we are hearing about frequency, which is not same as that of the local clock. So the frequency of the signal is nominally same as that of the local clock, but yet a slight difference is there between the frequency of the local clock and the signal of interest, right? So if you can see, this situation can emerge when we have two different crystal oscillators. This situation is not at all easy because most of the time, even if it is the same chip, even if it is in the same board or in the same system, we use most of the time single crystal oscillator. We don't use multiple crystal oscillators just because of different requirements. But there are situations of long length communication systems, long haul communication systems, where we may use multiple crystal oscillators. In those situations, this becomes very important, and that is where this timing recovery and a FIFO buffer is needed. So this is an originating module some thousands of kilometers away from this receiving module. Just assume that, right? It's a digital communication system. So this sends data, but this guy doesn't know when he sends. Anyway, there is a close relationship between this and this with respect to frequency, but it's not exactly same. So there is a timing recovery which recovers the frequency of this originating module and feeds into this FIFO buffer. So this buffer should be large enough to handle the data if it is sent fast or very slow. If the originating module sends the data very fast, then this buffer may overflow and it may lose some data. Or if it sends the signal very slowly, then there might be multiple copies, redundant copies of the same thing at the receiving module. Those signals that are not at all slave to the local clock and thus can transition arbitrarily are called as asynchronous interconnects. But even though asynchronous logic is much faster than synchronous logic because it does not slave to any signal within the circuit, and it can transition arbitrarily, so it can happen so fast. The response to the stimulus from the asynchronous circuit is very fast. It is always possible to synchronize asynchronous signals, but it is a complicated circuit. We might have to have this handshaking signals, which is a request and acknowledgement circuit. So this is interconnect circuit, which interconnects with the synchronous logic. If there is a data transfer needed from one block to another block, let me take the list pointer again. Yeah, if there is a data transfer between this module to this module, then what happens is it generates the data and asserts this DV, that is data valid signal. Once this data valid signal is generated, then it goes for handshaking with this module, right? If the handshaking is successful, then it initializes, that is it sends the I signal, which is the initialization signal for the data transfer. So after initialization signal has been sent, the data transfer happens between this register to this register. So this is how the data transfer happens in asynchronous interconnect when it is interfaced with the synchronous interconnect. Asynchronous design approach is very efficient in terms of computation speed because it happens at a native computation speed, which is much faster than the frequency of the clock, which is the periodic synchronization signal. But the problem is, you can see there are a lot of complex logics to make them synchronize. So when we interface an asynchronous system, for example your flash drive, if you insert it into the laptop, the data transfer happens between that asynchronous circuit with the synchronous circuit through a protocol. There are different types of protocols for that. So in summary, we can say that asynchronous systems are much faster and much efficient with respect to their computation and speed, but they have complexity with respect to the area and the amount of logic needed. That's all for this video. I'll see you in the next video. Thank you so much for watching. Bye bye.